reproducibility and good coding practices and documentation take some time overhead and take a little bit of patience. But just 20% of the effort can really reap you 80% of the benefits.
Welcome to the Reproducibility Podcast, an open science podcast featuring early career researchers. I'm your host, Will Nyam, currently a postdoc at the University of Chicago, which is on the unceded lands of the Kickapoo, Peoria, Miami, and Potawatomi nations. In this episode, I'm co-hosting with Jan.
Hey, I'm a PhD fellow at the IT University of Copenhagen in Denmark.
And today, we're joined by a very special guest, Anna Trisovic.
Hi.
Would you like to introduce yourself?
Yes, absolutely. It's great to be here. My name is Anna Trisovic, and I am a research associate at Harvard University. I have two affiliations, one with the group at the School of Public Health called the National Studies on Air Pollution and Health, and the second with the Institute of Quantitative Social Science, or IQSS, at Harvard.
Great.
Cool.
So firstly, how are things for both of you? It's conference season, change of weather, things going all right?
I'm finally over my hay fever. So
Nice.
But you know how I'm currently looking for a grant for reproducibility, kind of, getting a little bit of money. Fostering transparency. Turns out the second biggest private funder in Denmark is Velox, the window people. So I think I'm going to write them an email because if one, company's interested in transparency, I hope it's the fucking window people. So
Very, very invested in transparency.
yeah, hope you'd think, right? So cross your fingers. We'll see how that goes.
That's so good. How are you, Anna?
I'm good, thank you. It's nice. The weather is starting to be nice, though it's very hectic in Boston. I feel we get a few days of hot weather and then we get a few days of cold weather. I don't have any conferences or grant proposals right now, but hopefully they will be later in the summer when the weather actually becomes nicer.
Mm-hmm. Yeah.
So you're all getting busy when there are those few nice warm days before it goes away again, you mean?
Yes, I don't know how it is in Denmark, but here definitely it's I feel like 2 days of hot weather and then we go back to the winter jackets or coats. So
no, we just have a lot of wind here, but you live.
Yeah, I remember I lived in Chicago a few years ago, and there at least the weather was also hectic, but then at least when it was winter, it was really cold and wintry, and the summer was somehow, there was, I think, more consistency.
Yeah, we're coming out of our winter now, and it's been a long winter, and everyone's just waiting for the summer. Anyway, we should probably get on to the episode on what we're actually talking about today, which is we're going to be talking about good coding practices. Moving on to our first segment, which is our appetizer. We're trying to sort of focus on best coding practices for computational reproducibility, which I think is an important feature of replicable science. Being able to execute the research code or the scripts that run the experiments or the code that conducts statistical analysis, having those things be re-executable seems to be a really important component of reproducible science. So our appetizer is a notable paper by our special guest, published in 2022, called A Large-Scale Study on Research Code Quality and Execution. Do you want to give us a quick rundown of that paper? Maybe the story behind it or how it came about?
Yeah, absolutely. It was a very interesting paper, very interesting to work with, and also had interesting outcomes. So the motivation behind the paper was just the fact that now more and more sciences are moving toward computational research. So everything is done with the research code and on computers, right? More sciences have big data. So I was working with IQSS with the Dataverse team. So that's a data repository. And we noticed that more and more data sets, which are the bundles of data and code, have code files. So it was not just about sharing data, it was about sharing both data and code. Mm-hmm. Even though the word dataverse comes from like universe of data, right? So essentially, 10 years ago, we had less than, or maybe 10% of the data sets containing code files. And today that number is almost like 40% of the data sets contain some code files. Mm-hmm. So we wanted to learn more about these replication packages. So there are two ideas, two motivation points. The first one is that we wanted to learn how they are documented, how the code is structured, what is kind of like the nature of these files, are they big or small. And the second is we wanted to learn what is the quality of code or re-execution or reproducibility, reuse of these files. And also we wanted to classify these datasets in different categories and wanted to see like how each field of study is doing and how different collections, maybe journal collections, are doing in comparison to other datasets on average. And it turns out the journal datasets are doing much better, and we will learn more about that hopefully later.
Yeah, definitely. So for our listeners, I think go ahead and browse the article and have a read through. There's a lot in there, so it's worth definitely checking out. And yeah, I think hopefully by the end of this discussion, we'll get to some ideas about how we can improve our coding practices. Hopefully we'll get to that. Yeah, so let's talk about what did you find in terms of what barriers to code quality? What did you see in your study?
Yeah, we saw a lot of things. So essentially, the experimental setup is such that we retrieve each dataset in a computational workflow that was implemented on AWS. Yeah, there are over thousands of these kind of shared datasets. We retrieve each of them on AWS, and then first we look into the dataset itself. We see if there are any documentation files. We see how many code files there are. We see what is the nature of this code. Are there any comments or not? What are the file names? Are they long or short, descriptive or not? And how big is the data set? And then, so first we collect that information, and then the second part is that we try to do the re-execution of these code files. And then depending on whether it is successful or not, if it is successful, we just write down that result. But if it is not, we conduct automatic code cleaning. So we try to solve the problem by installing potentially other libraries for the code, or by removing some of the fixed paths or things like that. And then after automatic code cleaning, we try to re-execute the code files again. And then that's where the experiment essentially ends. We record both success and an error. But we also try to do the same experiment for each file using several different versions of software. And in particular here we use R. So we will use 3 different versions of R, and in each we will have automatic code cleaning if the code execution fails.
So let me try and understand. So the automatic code cleaning is like a script that you run to help clean up the code of the existing code in these data repositories that have been uploaded. Like that might like install packages or do something like that to help resolve some common errors. Is that right?
Yes, that's completely right. And that is because there's some errors in code that are easy to solve. For example, there might be a fixed path, on your system. And then there is a command that can resolve this fixed path and then actually reference a file that is inside the dataset. So that is an example of an error that is easy to solve, and that can really improve the final result. Or, for example, installing the library, because sometimes people will run the code in an existing environment where they already have everything installed. So, for example, if we detect that there are missing libraries, we are going to install them, and then the codes in the second re-execution run, it will be able to use that library.
Yeah, that's so interesting. It's almost like it's like an automatic version of what I think peer reviewers or scientists should be doing, which is trying to re-execute other people's code and analyses to make sure their results are robust and reliable. So that's kind of fun.
Yeah, I think it is definitely. I think that reviewing research code, because by its nature, research code is very different than industry code, right? In industry, you have like always small increments of change in the code. You have testers, you have reviews, but then in research, we don't have that system typically. So typically, the nature of this code is very exploratory.
I mean, also in research, in development, you have professional programmers, and I wager to guess most of us researchers are not professional programmers. We kind of never had to deal with writing code that other people might have to read later.
Yes,
never
exactly.
got the training to do that.
Yeah.
And we always work with students, right? Students, they're like, okay, they might have some education on code practices and programming, but many will not have. So it is always kind of like starting from scratch.
Yeah. Okay. Yeah. So I can see with the code cleaning, it improved things a little bit, right?
Yes, definitely, it did. But then turns out then that so the old errors that we were trying to fix with code cleaning, they were masking new errors that we see again. So I think that somehow, yeah, whatever we do, there is always going to be this problem of code rot, meaning that just with time, research code and any other code that is kind of like stationary in time and not maintained will be harder and harder to re-execute and to reuse. So yeah, that's why I like to say that transparency is more important than reproducibility. So reproducibility, in how we define it right now, it's very binary, right? It can be either something can be either reproducible, we have the ability to re-execute code and the methods and get the result that was reported, or it is not reproducible. So somehow it's binary, and things should not be like that. I feel that, it's also depending on how much time you want to invest in reproducing a published study. The more time, the more likely you are to reproduce it, to do it. But then on the other hand side, we can aim to have transparent code and transparent results. And then by having something be transparent and understandable, another person, for example, you guys, would be able to follow my code from the first line to the last and just maybe rewrite it in a different software version or a different programming language and just be able to understand what was happening and what was the whole logic. So I think that transparency should be like a long-term strategy for science.
Yeah. It's still surprising that even with this, like, let's say, binary re-executable metric, only 25% success rate without code cleaning and then 40% with code cleaning. Although I see that you also have 56% of code was successful with both code cleaning, right? Well, best of both. So is that surprising to you? That, like, to me, that's a very, maybe, I don't know, maybe less than what I thought should be re-executable, maybe more, I don't know.
It was definitely very interesting. And of course, yes, I was happy that we were able to increase the re-execution rate by that much just with automatic code cleaning. So yeah, definitely that was interesting. Though, of course, we discussed this as a limitation of the study. We re-execute the code. We don't know often what script goes first, what goes second. Typically, datasets will have like 1 or 2 or 3 code scripts. So then we are likely to actually re-execute the first one first, or the only one first. But then sometimes we will have also errors coming from just maybe trying to re-execute the second script first or so on. But then, yes, it definitely, without code cleaning, the re-execution rate was on average 25%, which is pretty low. But then, yeah, with code cleaning, that was a big increase to 40%, which just also shows that some small changes in code can really make a big difference. Just avoiding fixed paths, installing libraries, defining them early on, can make a big difference. So I think that's good news for us.
Yeah.
So how often did you, like, especially when there are more than one data file, analysis file, how often did you find like README files or other kind of meta information that would help you analyze it?
Yeah, that's a great question. And that is, the first part of the study. One of the key things was how well described are these data sets? Do we have documentation? What are the meta information? So yes, and we have some good results to present. So essentially, on average, we find that almost 60% of the data sets had some documentation. That took some time to how we define documentation files. So these are definitely READMEs. There are also code books and other files. So there are different ways in which people write their documentation. So we were trying to be very inclusive and look for all sorts of different documentation files. And yes, they were present almost in 60% of the data sets.
Okay,
the second thing is that, that's really good. And I think that, the second thing is also that we noticed that file name lengths were quite long. So from 10 to 20 characters, which is also descriptive and telling, and you're more likely to understand what these files are if they have a descriptive and a good name.
Yeah,
and also,
I have to get better at that.
Definitely, that is so useful.
All my experiment files, I'll write my analysis file might be like analysis model comparison or analysis and then I'll have multiple analysis model comparisons on my computer, and I'm like, wait, which file am I meant to be using for this experiment or this project or so on and so forth? I need to get better at file names.
Yeah, I think that is maybe one of the main advices I was given, and I would also give to have like a good file name. I think that is also, for science, but also like just for everyday life. I remember I was like looking for a tax file from last year, and I just couldn't find it for my life. And then had I named it better, it would have been searchable and so easy to find. Yeah, so that was very frustrating, could lead to a waste of time unless you think about that in advance. So that is definitely an advice that we should
take to heart.
We'll come back to
the next section.
We'll recap to it. Yeah, we'll come back to it. But yeah, that's fun. Okay. Yeah, what else did you learn about trying to re-execute everyone's code?
Yeah, there were many interesting things. For example, code re-execution is directly dependent on libraries used in the code. So yes, we were able also to study what libraries people use. And yes, of course, most for data science will use visualization, plotting, data wrangling, statistical analysis libraries. But we were also curious whether scientists use some of the libraries that are considered to be libraries for good coding practices. And these libraries include, code testing or runtime environment libraries or workflow libraries. And turns out we could not find like almost any single use of this good libraries. So that was surprising.
So is the implication that scientists are writing a bunch of code for their projects but not testing their code, like not running unit tests in their code and not doing this kind of stuff for their experiments and things, like for their projects?
Yes, I'm afraid that's the case. Though I think I think that there are other ways to test code, right? Maybe they will. Sure. So yes, maybe they will write many, prints statements everywhere in the code, or they will write many comments. We do see comments in code very frequently. So I think on average there are 20% of a code file is comments, which is like pretty high. I think definitely much higher than what is considered normal in the industry. But of course, this is debatable. But yes, definitely something that we would consider to be good coding practices like unit tests. We do not see that in research code. It just also shows the nature of research code, the exploratory nature, something that we already touched upon.
Yeah, and also directly reflects on the lack of training that scientists get on like code development, like writing functions that are unit tested or are maintained and so on and so forth within the experimental setting, in experimental context. Yeah, it's interesting. There's some places to improve. One of the reasons I came past this study was it was shared a lot on Twitter was because of a figure where it showed the re-execution rate per field of study. And, for example, we saw like in the social sciences, it was about 40% success rate for execution. Did you notice any differences between like subdomains or research domains, things like that?
Yes, we report on that. And there are many datasets belonging to different fields of study. So obviously social sciences and then other sciences. But what is important to mention here is that Dataverse was initially created as a data repository for social sciences. So most of the datasets actually belong to social sciences. And then only later on, it changed its focus from a social science data repository to general purpose data repository. So though it was a natural question for us to ask what is the re-execution rate per field of study, it does not really give us a full picture on what the actual rates are. So it's a good figure, it's a good discussion, it's a good question to ask, I think. But because of our sample is coming from social sciences, we are not able to really get the full picture. So for example, I want to emphasize that some of the other sciences like physics, our sample is very small. It is like less than 20 samples, whereas social sciences, we have like almost 3,000 data sets. So yeah, it's an interesting picture, but we need to like really be careful how we talk about that.
You also looked at the Harvard Dataverse, right? Which is that exclusive to Harvard researchers, or who is using it?
It is. So Harvard Dataverse is one of the Dataverse repositories. So there are Dataverse installations all over the globe. Harvard Dataverse is the biggest one and the first one that was deployed. However, it is not only used at Harvard. It can be used by anyone who wants to publish their datasets. And then in particular, there are collaborations in between Harvard Dataverse and journals, different journals that have their own collections in Harvard Dataverse. So journals can publish their dataset collections in Harvard Dataverse. Also, anyone at Harvard can publish their datasets at Dataverse, but also any other researcher or scientist worldwide can decide if they want to have their own collection and publish their datasets in Harvard Dataverse. So it is open to public. There are some, of course, you cannot just release anything. It needs to be a dataset that is related to science. But yeah, it is open and it is the biggest installation. That's why we did the study there.
Yeah, there's a lot of data sets and a lot of data files to sift through for this paper. So yeah, it's I think it really does capture a cross section of science. Like yes, there's I guess we can say it really captures what's happening in social sciences, at least in psychology and maybe economics and so on and so forth, where we're seeing not all the code is being re-executable and reproducible, and so maybe we should focus on trying to improve the codes in this area. Yeah.
Yeah, I mean, I wish we could say that in this study. Just like pointing out to different fields of study and telling, yeah, or we have evidence to think that you can improve here and here.
Right.
But
right.
in this particular case, though, I've also seen this plot, like the
Yes.
plot with different fields of study on Twitter. It does not tell us a full picture. I think,
Right.
but there is one result that I like to talk about, and that is actually exciting and telling.
Yeah,
And I
go
think
for it.
that's like my favorite result from this study.
Yeah.
So I mentioned that different scientific journals have collections in Harvard Dataverse. Turns out that on average, we can see that the data sets belonging in journal collections have higher re-execution rate than other data sets. That means that journals do something better than average. And when we look a little bit more close, well, maybe, yeah, when we look a little bit more closely into that, we can classify different journals according to their data sharing policy. So journals have, in the last decade or maybe longer, decided to introduce a data sharing policy, essentially requiring their authors to share data and code together with the paper. And some journals have flexible policy, saying that journals are encouraged maybe to share their data set, but some have stricter data policies, saying that not the journals, but the authors are encouraged, or in this case required, to share their data sets. Or in other cases, the journals say that the data sets will be reviewed or verified. So not only that the authors are required to share data and code, but this will be reviewed and verified. Turns out that the strictness of the policy is correlated with the success rate, with the re-execution success rate. Or in other words, the stricter the policy, the more re-executable results, which I think is really interesting. That really presents evidence that the data sharing policy strictness is conducive or helpful in code re-execution and code reusability. So yes, that's great for the journals. I think that's
Right. I wonder, number one, how many journals are doing the review and verification and incorporating that strictness into their policy. But it is a good sign that these kind of policies or whatever they're implementing does seem to improve the re-execution of the code files. That's pretty cool. I just wonder how many journals were gonna value that in their setup.
Well, yeah, okay, we don't have that many, so maybe we have 2 or 3 that have very strict policies. For example, political analysis, AJPS is the 2 that have the highest policy strictness. But then, yeah, there are other ones that maybe just encourage authors to share their data and code, and still we can see improvement. So I think that's definitely a step in good direction.
In the right direction, yeah.
Yeah.
I'm just thinking within like psychology and the premier journals in psychology, I think most of them they have encouraging policies. They don't really have they don't require data be shared or code be shared. It's sort of the classic materials will be made available upon request kind of situation. So it's interesting. Maybe journals should take more of a stand towards trying to include re-execution of code in their acceptance criteria or in their review criteria.
Yeah, that's definitely what this study shows.
Yeah, nice. I guess this is a good spot to maybe talk about because at the end of your paper you talk about what could be improved upon, like what are some good practices for coding that might help research code be re-executable. Do you want to go through some of those recommendations?
Yes, absolutely. So we do have several recommendations for scientists, for journals, repositories also. at the end of the paper. So I think that's the favorite part of the paper. But then also I have some that are just kind of like useful from my own experience and that we already mentioned. So maybe the first one I will reiterate is name your files in a good way. Whether that's a text file or a code file, it should have a good name. I think maybe a good practice is also to have some sort of like numbering scheme. So, calling your pre-processing files like 1 or 1,000 or 100, denoting whether it should be executed first, second, or last.
Oh, I see. Right. What is an example of a good like file name? Like what should we avoid and what should we include in our descriptive file names?
Well, okay, I mentioned if you have several code files that then chain one after the other one, you can decide to call all of your pre-processing data files with a prefix 100 and then have like 101, 102, 103, or
So would you
or like
recommend rather
110,
having...
120.
Sorry. Would you recommend rather having one large file that you can run from start to end, and then you go from data cleaning all the way to your final t-test? Or would you say more smaller files to see all the intermittent steps?
Yeah, I think that having smaller files is good. Smaller files that have good names is better to understand the flow. That's called like a higher modularity, right? So it is then easier to potentially understand what each script is doing.
Okay.
But I think, this is not like very black and white. In some cases, maybe having like one long file, it's going to be easier.
Yeah. What else? What other code practices do you think would be that researchers would benefit from implementing?
When studying the code from Harvard Dataverse, we see many of the code files look like a wall of text. And that happens when one line of code is then repeated many, many times. And then you like literally get like a wall of text. So my recommendation would be don't copy your code. Don't copy and paste your code, but just copy it and create the function.
Yeah, write a function.
Write a function, exactly.
I look back at my old code when I was starting in science, and for example, a classic one was I would have different scripts creating different figures. Like they were all bar plots, but I would like copy and paste the same bar plot code over and over and over and over and over. And I could have just written a function that was like create bar plot and just called that function without writing this code 1,000 times. And it's really important because if you hard code any variables into these copy and paste code, you have to change it in every iteration that you've copied and pasted. So if you change a variable name or whatever, you've got to go through, and that's a common place to make a mistake where you forget to change or you miss a place like you didn't change the right variable, and then all of a sudden you're trying to find an error that you put into the code that isn't going to spit out an error message because it's still executing. You just don't know. You just haven't changed the variable. You haven't checked the variable names and such. So yeah,
exactly.
I learned that one the hard way. Definitely write functions when you can.
Yeah, 100%. I just agree. That's like such a typical spot to make mistake because you just forget to change some small variable, and then like you have a potentially an error in your code. So definitely, I think, and plots are some of the nicest places to parameterize by passing these variables of what you want to plot, and then you're able to loop through different variables or different things, and then just having many plots at once. Yeah, so definitely that's a good idea.
Yeah, likewise, especially with plots, I found that putting all the design elements, defining them at the very beginning of my analysis file, allows me to very quickly cycle through some designs, like adjusting the colors of the plots when I find that, this doesn't work quite out. it can save you a lot of time.
Yeah, and I have to mention now, like I'm going to whole new recommendation for code practices. I think that the key one that this study teaches us is to capture your code dependencies. So I think that's the key one, the one that I think is most significant when it comes to reproducibility and reuse and code re-execution. Understanding
what does that mean? Like what? Just for some of our listeners who might not be more familiar with computer science or the code that they're writing now, their early career, for example. What do you mean by code dependencies?
Absolutely. So you have your script, and it will likely work with one or more programming language versions that you used. So, for example, in R, it is important to capture what version of R you used. And you're likely also using other libraries. So you're installing, plotting libraries or other libraries. So it is important to keep information of these libraries and their version, because these libraries are often not really compatible with one another, and sometimes will create a conflict, and you will not be able to recreate the same environment unless you capture the libraries that you used. So that's a really significant thing.
Yeah.
Python does this really well. So having a whole new virtual environment as a workspace where you can be totally in control of what libraries you use and what Python version you use.
Yeah. How do you capture your code dependencies? Like, what should a researcher do to make sure that happens?
So, for example, in Python, that's relatively easy. There is pip freeze command where you can export your used libraries and their versions. And typically, the way how these are exported in a file called requirements.txt, and then one can, the same very easy using pip, install that libraries from requirements.txt file.
So, you mentioned virtual environments. So for those who might not be let's say familiar with what that is, because I only learned about virtual environments maybe not so long ago. That's like being able to set up a new, fresh, computer on your machine so that they can run the experiment just by setting up that same virtual environment or downloading that virtual environment, let's say, so that you can run the code exactly the way that you ran it, for example. Is that a good explanation of virtual environments?
I would even say it's easier than that. It's not like a whole new computer. I think it sounds intimidating, but then they are really not. Because most of the time, I use virtual environments in the same folder as my analysis study, and they can be activated or deactivated, and then you always have, for that particular study, all the dependencies that you need. So I think, one thing that I would say here is that they might sound intimidating, but the truth is that this is just like maybe no more than 4 or 5 lines of code that you always use. So creating your environment, activating, deactivating it, exporting it, and installing things in it. And that's pretty much it.
Yeah, what do you think about setting up Dockers for your environments and things like that? Is that a good step to go?
Yes, definitely. So that's maybe like a next step. The way how I think about it is that if you use a single programming language, say Python, you can just use Python environments, and I think that will be good enough in most cases. But then if you use multiple programming languages, if you need some other software for your study, you should consider using Docker containers.
Cool. I want to stress to our audience that a lot of these benefits that come from doing all of these good coding practices are actually you gain the benefits. So for example, we talked about how naming files descriptive saves you time, because in the future when you forget about the code that you're writing, you can go search it up and find it and things like that. And it's we at our UChicago reproducibility group, we had a little coding session, one of the computer science researchers, PhD students, who's a whiz at coding, kind of like went through all of this for us, and he talked about this rule. So shout out to John Villette. He talked about this like 20-80 rule. Like you just put in 20% of extra effort to make your code better and reproducible and whatever, and the benefits are like 80%. you get so much return on those improvements because you are the one that's looking at your code all the time and so on and so forth. Yes, I highly recommend our audience to invest time in this. It's well worth it.
I do not appreciate but understand how long it took for you to say people after computer scientists.
I was trying to find the correct descriptor, but I couldn't find it in my head though, in enough time. Yeah, no, so like I think one thing we haven't touched upon is writing comments. You mentioned like in your study you saw like 60% of the code were comments.
Not that many. Not 60. I think maybe around 20%.
Oh, 20%. 20% of code was comments. So yeah, I think another tip for our audience is to write comments while you're writing the code, because that's when you're thinking most about the code, so you'll remember what you're trying to do and what you're doing, rather than not doing it, rushing to the results or the data or the analyses to present to your supervisor, and then coming back to code and forgetting what each line does or how you set it up.
Absolutely, but also, having an intuitive variable name is also as good as having a code line comment. So I would think, try to have intuitive variable names, but then if that doesn't work, add a comment on what the line does or what that piece of code does. But then additional advice, I would say, try to seek code review. Like ask your peers or co-workers to review your code. They will probably point out some things in the code that you were overlooking. Maybe they will find a small mistake, or they will, or they might point out some things that should be better documented.
I find it so intimidating. Like it's still scary when you go ask someone to look at your code, because like, please, like I know sometimes this might not be the best code in the world, but like please review it and like be kind. Tell me how I can make this code better. But it's really helpful. It catches not just like errors. That's not the main goal. Like that's not the only goal of code review. It's like is your code readable? Is it transparent? Could you get it to work? Does it make sense? All this stuff all these questions can be answered through code review. Do either of you have good experiences with code review?
I think. Somehow it can be very frustrating to review research code. In industry, you have always like small increments of code, and they're constantly reviewed and tested, and then multiple people know exactly what the code base does. But then in science, the nature of programming is like exploratory coding. And then if someone reviews your code, that will likely be that you're already completely finished with it. It is a final product, and the other person, the reviewer, is supposed to somehow understand everything just by looking at it. So I was thinking that it must be like very frustrating to review a code that you have never seen before. And I was going through code reviews at the Journal of Open Source Software. So Journal of Open Source Software is a completely open source journal where you can publish your code, your software, in a 1, 2, 3 page papers. So the aim is to promote research software and just generally software as a first-class product in science, and to facilitate software citation. So the thing is, with a paper description of your research code, you would submit your research code, source code, and reviewers are expected to review both the paper and code. And I was thinking that reviewers might be frustrated because they see this code for the first time and they're somehow expected to understand what it does. And looking through these reviews, the sentiment is actually quite positive, or definitely it's not negative. Even though like my primary hypothesis was that it would be negative. So that was surprising, and I think a positive result. Of course, I think that people will not, just out of the blue share negative comments in this context. But still, the sentiment was mostly positive.
That's really good. That's encouraging. I think a lot of things around computing science and computing practices are daunting. Like, it's vulnerable. Like, you're putting your code up and for people to look at and to criticize, I suppose. But it's nice to know that it's there's positive. It's mostly positive and mostly trying to improve the code and help. Any last pieces of advice for our early career audience regarding their coding practices?
I think we went through everything that I want to emphasize.
We can do a quick review.
Yeah.
So file names that are descriptive and maybe indicate the order through a numbering system. Descriptive variable names as well, even in place of comments. So if you have a good descriptive variable name, maybe you don't need the comment. But also comment as you code so that you remember what you're doing. Think about your code dependencies. Try and make sure you know what libraries and what package versions or software versions you're using and have that saved somewhere, maybe using
don't copy
freeze.
And paste your code, but copy and create a function.
Yeah. Yes, write a function. Yes, thank you for the reminder. I need to do that myself. Make sure you write functions instead of copying and pasting code everywhere.
Like ask someone to have a look at your code.
Yes, code.
That's also what we see in the study is that the journals that have some code review had better results.
Yeah. Cool. That's great. So hopefully our early career researcher audience is, empowered to go take this on. It's worth it, I promise. It's worth putting it.
Definitely. I mean, there are also other recommendations in the paper itself. I also encourage everyone to check those out.
Yeah, nice.
We could not cover everything just now.
That's a lot. A lot can be done. But remember, just 20% will give you 80% return. It's worth it.
One thing I would like to... well, it's not really a recommendation for your code, but I think it kind of falls into a similar thing. Cite the packages that you use. Especially if you're using R, you can just type in citation and then the package name, and you get both the citation that you can put in your paper if your package contributed, if a package contributed to it, and that also tells you the version of the package you're currently using. And one thing I recently found, that's why this is on my mind, there is this R package called Grateful, which basically you use the main command of it, which is cite packages, and it just throws you out all the packages that you're using that you have currently loaded into a nice bib file, and you can copy that into your own, and then you have all the citations and versions ready of everything that you used.
Wow, amazing.
That's great. I'll have to check that out.
Yeah,
I think that
looks really useful.
Really cool.
And you're also helping all the people who contributed to those packages get some attribution.
Yes, exactly.
I think that's great. Yeah.
Do we have anything else we want to cover or share?
Maybe for the last segment of the podcast, I would say that reproducibility and good coding practices and documentation take some time overhead and take a little bit of patience. But then I will conclude with a sentence that you repeated, Will, a few times, is that just 20% of the effort can really get you 80% of the benefits. So definitely worth it.
Yeah.
That's a really good closing statement.
All right. Do you want to share with our audience where they can follow you or find you, Anna?
Yes, I am on all social media. On LinkedIn and Twitter, in GitHub. So my handles are everywhere A Trisovic or A Trisovic. So the first letter of my name and then the surname.
Great.
I love the French pronunciation.
Okay. Yeah. Jan, where can we find you?
So you can find me primarily on Mastodon at vornhagenjb at hci.social.
And I am on Twitter while it's syncing at Wilnyam, and also at Mastodon, Wilnyam at fediscience.org. And I'm going to shout out my GitHub because I've never shouted out my GitHub. There's not much on there, but I'm at William Nyam on GitHub. Yeah, hope that was useful. Thank you for listening. Catch you next time.
It was really great to talk to you guys.
Yeah, thanks for being here, Anna.
Thank you.
Bye, everybody.
Bye.
Bye.